Let me begin by stating the axiomatic characterization of the Riemann integral again before we go to the proof. Theorem is as follows. Let a comma b in R, a greater than b. Let f be a continuous function on closed interval ab. Suppose that on each such function we can assign a number IAB of f that satisfies number 1, if small m is less than or equal to f of x is less than or equal to capital M for all x in closed AB, then m into b minus a is less than or equal to IAB of f is less than or equal to capital M into b minus a. And property 2 is for all c in the closed interval AB, IAB of f is nothing but IAC of f plus ICB of f. Okay. Needless to say, this function IAB is defined on all continuous functions defined on closed interval AB. I am assuming that given any closed interval, there is an associated I function that sort of is supposed to measure the area. Okay, so the way I have written, you might be misled into thinking that this IAB function is defined specifically for this particular pair AB, but that's not the case. For each continuous function on any closed interval, there is an associated function. Okay, then the function x going to IAX of f is differentiable in the interval AB, and its derivative is small f of x. So if you differentiate the integral, you are supposed to get back the function. That's what this is saying. Though we don't really know what this IAB of f is so far, it is just something that is assumed to exist and satisfying these two properties. The proof for all the build up with the statement is actually quite easy. Proof. So for instance, what we will do is we will first take h to be greater than 0. The h less than 0 case is exactly similar. Word for word, you just have to change a few signs and everything will drop out in your lap. I leave it to you. What we have to do is find I of a x plus h of f minus I a x of f divided by h. This is the Newton quotient. We are going to compute the Newton quotient by hand. Okay. Now here is where things get a bit helpful because we have properties. We have the properties that we need. We can write IA x plus h as IA x of f plus IX x plus h minus IA x of f. This is just by property 2 of the function IAB or IAX here. And immediately we see that something nice happens. We are left with IX x plus h f of h. Okay. Now on x plus h, you are understanding why I have taken h greater than 0 now, so that proof becomes easier to write down. Exactly similar arguments will hold when h is less than 0. We can find let's say s and t such that f of s is minima and f of t is maxima of f restricted to this closed interval. On any closed interval, continuous functions attain maxima and minima. I am just choosing the corresponding points to be s and t. Okay. So what does this mean? We know that by property 1, we know that m, or rather f of s times h is less than or equal to x plus h of f is less than or equal to f of t times h. This is just property 2. This is just property 1. Okay. Now that means f of s is less than or equal to x plus h comma f by h is less than or equal to f of t. Okay. Now note that you might be deceived into thinking that this s and t are constant, but technically s and t depend on h. But f is continuous. So as h goes to 0, both s and t converge to the point x, right? So this is saying nothing essentially. You have x plus h. Okay, you have chosen the points s and t somewhere in this interval. Okay, as x plus h converges to x, these points s and t will have to go to x, and this just follows by continuity of the function f. This is the place where we have used the continuity crucially. Okay, now I want you to justify this rigorously. Okay, and figure out what happens if f is not continuous. Figure out what happens if f is not continuous. Okay, therefore limit h going to 0, I of x plus h of f by h converges to f of x. Because it is sort of squeezed between f of s and f of t, and both f of s and f of t sort of approach x, both s and t, oh wait a second, I might have misled you a bit. Both s and t converge to x. That's not dependent on continuity. That just follows because s and t are squeezed between x and h. What is actually continuity is going to say is that f of t and f of s converge to f of x. Okay, this is the part that requires continuity. Okay, this is the part that requires continuity. So let me just erase but as h converges to 0, both s and t converge to f of x. Therefore because f and t and f of s are continuous, f is continuous, f of t and f of s both converge to f of x. This is the part I want you to rigorously justify. This is actually just one line. Okay, so what requires continuity is the fact that f of s and f of t both converge to f of x, and this delivers the proof. This is the proof. That's all. The proof is so simple. This is the proof. Okay, so we have now gotten a proof that this function I, which is modeled on the area function, but doesn't seem to satisfy all the requirements that we listed out of area. Just seems to satisfy some basic requirements like this additivity, which is very basic, and the fact that if you can squeeze in a smaller rectangle and a larger rectangle inside and outside the region, then the area of the rectangles, you should have this relationship. These are obvious things that you require of area. Just with these requirements, you have something like the fundamental theorem of calculus. Okay. Now let's try to geometrically interpret what this is trying to say. Okay. So what I will do is I'm going to borrow this figure from Wikipedia. So this is courtesy Wikipedia. Courtesy Wikipedia. Okay, I'm just borrowing this figure and let's try to see what it's trying to say. Okay, so you have this graph of this continuous function y equal to f of x. Okay, and for each point x, so this is going from let's say it's starting at 0 and going all the way somewhere let's say till 1. Okay, now what we are assuming is that you have this function area equal to defined to be a of x, which is supposed to be area under the graph of f in 0x. Okay, so you have a function that measures the area. In our notation, this is supposed to be captured, but we have not yet even constructed it, but it's supposed to be captured by I0x of f. Is essentially the function we considered. Okay, so we are assuming we have an area function. This function I will turn out to be the area, which we will see in the construction in the next lecture. Now let's see what happens, why geometrically you would expect this area function to be related to the derivative. Okay, now notice that if you want to compute area of x plus h minus area of x, which is what we were interested in, what you can do is you can just take it as area of x approximately equal to, I will use this tilde notation, approximately equal to a of x plus that red portion, right? So a of x plus h will be nothing but a of x plus the area of the red portion in this picture. Now that red portion area, this is not approximately equal to, this is exactly equal to. Now this red portion is approximately equal to f of x into h, right? This is just f of x into h. In fact, we can write it as f of x into h plus excess portion, what they have called excess, this part. Okay, this is the excess portion. Fine. So we have written down a of x plus h minus a of x as f of xh plus the excess portion. Okay, now it's really easy to see why areas is related to the derivative. All we are doing is we are taking a of x plus h minus a of x by h is equal to f of x by excess by h. And what is really happening is, by continuity, this goes to 0. This goes to 0 as h goes to 0. Right? That's essentially the entirety of the proof. Okay? And the rigorous justification that the excess portion does indeed, excess portion divided by h does indeed go to 0 is what we have just presented. Except the I function that we have, we don't know whether it's the area. It's just a function that has two basic properties. Okay. Now, why would you expect this I function, whose existence itself is yet to be shown, is actually going to measure the area, since it satisfies only two basic requirements of area, not all? Well, this next corollary with this geometric interpretation that we have should convince you If it doesn't, don't worry. In the next lecture, when I'm going to rigorously construct this I function using Riemann sums, upper sum, lower sum, and so on, it will become geometrically obvious that in fact, yes, this I function is in fact going to measure the area. Okay. Let I be the association, be an association, that's a better way to put it, be an association. Note, there could be many functions so far. All I'm saying is, given any closed interval and a continuous function on that closed interval, there is some way to assign a number IAB of f. There could be more than one way that satisfies conditions 1 and 2 that we have stated in the previous theorem. Let I be an association as in the previous theorem, then I is uniquely determined. There is only one such function. So from combining with the previous geometrical argument, we have to note that if at all there is an I function that exists, it's got to measure the area. This is made more precise in the second part. If capital F is differentiable on closed interval AB, then if capital F prime is small f, we have, as you can expect, IAB of small f is just capital F of B minus capital F of A. Okay, so what we get is the following. If at all there is an association I, then IAB of small f should be capital F of B minus F of A. It must sort of satisfy the fundamental theorem of calculus. This is the fundamental theorem of calculus. I mean, the conclusions of the previous part and the conclusions of this part are sort of two versions of the fundamental theorem of calculus. And if you think about it, with this geometrical interpretation that we just saw, it will sort of force this function IAB of f to be the area under the graph function. Okay, so this is something that you have to realize for yourself. Me coming and explaining for 15 minutes repeatedly is not really going to make an impact. I urge you to sit down, look through this geometric interpretation, look through the proof of the previous theorem and the proof of this corollary, which is just 2 lines. Proof. Okay. Now, by previous theorem, capital F and x going to IAX of f have the same derivative, right? That's what we showed, have the same derivative. Okay. Now, if two functions have the same derivative, then you can show that f of x, capital F of x, should be IAX of f plus some constant y. This is just one line from a rather important theorem that we saw in the chapter on derivatives. It's going to be rather easy to show this. Okay. So capital F of x is just IAX of f plus c. Now set x equal to a. Okay. So you will get f of a is equal to IAA of f plus c. But IAA of f should be 0. This is by property 1. Okay. By property 1, IAA of f is 0. So we get c equal to f of a. So in other words, IAB of f will be just f of, so this would be small f. IAB of small f is just capital F of B minus capital F of A. Hence proved. Okay. So this is really interesting. This is really interesting. We have now shown this function IAX of f, whose existence is still up in the air, seems to be the candidate for the area under the graph function. So our goal in the next lecture is to give a proper construction of this function IAX of f. This is a course on real analysis, and you have just watched the module on the proof of the axiomatic characterization of the Riemann integral.